Hi everyone, I'm Yuqing. I will briefly summarize a line of my works that propose an information-theoretic framework for both information elicitation and semi-supervised learning. So these works actually touch three areas. One is information theory, another two is, I mentioned before, information elicitation and machine learning. So let's start from information theory basics. So here you just need to understand the intuition. The formula is not important. So for a random variable x, the entropy of x can be understood as uncertainty of x. So for example, if x is a binary variable and with 50% probability it will be 0, in this case, there are a lot of uncertainty here, and x has large entropy. And another case is like this x prime, with 99 probability it will be 0. So in this case, it's actually very small amount of uncertainty here. So this x prime has very low entropy. And here is a formula of the entropy here, if you can refer to this formula here. And another important concept is this conditional entropy. So it just means that when we have two random variables, x and y, so the conditional entropy can be understood as conditioning on y, what is the remaining amount of remaining uncertainty of x. So in this case, if x is always equal to y, and conditioning on y, you also know x as well. And in this case, there is no uncertainty here. And the conditional entropy of x conditioning on x is always 0, which is actually the lowest. So still I put the formula here, but it is actually not important. You just need to understand the intuition here. And here is a set visualization of this basics. So basically we have two random variables x and y, and we can use the area of this circle to represent the entropy, the amount of uncertainty of x. And we can use area of this part to represent the conditional entropy of x conditioning on y. And the most important thing is this intersection area. We can use the area of this part to represent the mutual information between x and y. So it can also be seen as like the difference between the uncertainty of x and like the conditioning on uncertainty of x conditioning on y. And still I give you a more intuitive formula here. So basically the mutual information between two random variables can be understood as a correlation between them. It doesn't matter they are positively correlated or negatively correlated. So if x and y are independent, there is no correlation there. And in this case, we can see the joint distribution always equal to the product of the marginal distribution. And intuitively, we can just use the distance between the joint distribution and the product of the marginal distribution to represent the correlation, the mutual information between x and y. And specifically, if you pick this distance measure as KL, the commonly used KL divergence, I put the formula here, it actually measures some like distance or divergence between two distributions. And if you use KL, and then this formula becomes the Shannon mutual information. Okay, so why we care about the Shannon mutual information? Just because it satisfies a very important property which we call information monotonicity, or you can call it data processing inequality. So still, it just means that give you these two random variables x and y, if you perform some if you process this data x, and the processing method is actually independent of y, in this case you will reduce their mutual information. And still here is a example here. So basically, it's just a conceptual example. So if you have a smiling face, this emoji, and if you like doing some processing this image, and in this case, the mutual information between this processed emoji and the text of smile will be smaller than the original emoji and the text of smile. Okay, so we can see, like, because of this property, why we call it is information monotonicity is because this original emoji is actually more informative than this emoji, and in this case it has higher mutual information. So this is why we call it monotonicity here. Okay, so after we talk about some basics of information theory, let's start to introduce the area called information elicitation. So there is a requester, and she wants to elicit tomorrow's weather. And there is a person here, and she asks the person, like, what's the weather tomorrow, and what's your forecast? And this person will give his forecast, like, I think with 90% probability it will rain tomorrow. And in this case, this requester wants to incentivize this person to tell the truth about the forecast. So what she will do, she will promise that after one day, after the weather is revealed, she will use this outcome and this person's forecast to pay, in some sense, the accuracy of the forecast, and to incentivize this person to tell the truth. And this formula, we call it scoring rule. It has two inputs. One is outcome, another is the forecast. So in this binary example, the outcome can be 0 or 1, and the forecast is a binary vector, which is P0 and P1, and the sum is 1. And there are two different scoring rules here. The first one is a linear scoring rule. So basically, like, if it's sunny, and in this case, the requester will pay this person 10%. And another one is this log scoring rule. You add a log here, and for now, just forget about the negative thing about this log function. At least it's a monotone function. And we can see we can use this one as our scoring rule. We can also use this one as our scoring rule. But the problem is the linear scoring rule will fail to incentivize this person to tell the truth, but the log scoring rule will work here. And if you are interested in the answer, I suggest you first try to think about the problem by yourself, and then you can search for some literature about proper scoring rules. And this is information elicitation with verification. So why we call it with verification? Because the payment is made only after the outcome is revealed. But in some situation, like in this situation, so still the requester wants to elicit some information about a volcano. She wants to know whether this volcano will erupt after 10 years. And she wants to elicit this forecast from the crowds. And the crowds maybe give their forecast for the eruption of this volcano. And for this requester, she will have two problems in her mind. So the first one is, who is the expert? Like, whose forecast we can trust among these crowds. Another is like, how can she pay them to incentivize them to tell the truth? And here I want to emphasize here, it's not like the weather forecasting problem. You can review the outcome like tomorrow immediately and then pay them. Here, like this volcano case, is like you cannot wait until 10 years later to see whether this volcano erupt or not to pay them. If you want to pay them, you need to pay them now. But in this case, this scoring rule will take the crowd's forecast as input, The problem is there is no outcome. So that is why we call it without verification. And the problem is how to design this F here. And this problem is called information elicitation without verification. Its another name is peer prediction.